Okay, we're gonna be talking through the universal soil loss equation that's found on page 507 and equation 14.1. I'm just going to write it up here. A is equal to R, then K, then LS, then C, then P. Each one of these has it stands for a particular part of the formula, and this formula is used to predict predict how much soil we would lose by means of water erosion on a particular field, and it takes into account all the differences that you could put into or most of the differences that explain fields in one part of the country versus another part of the country. So a field that is in the southeast, say in Alabama, versus a field in Montana. What are the differences? Well, there's climate differences, right? There's soils that are completely different. There's ways that people produce crops that are different. So this model aims to take all those factors and kind of put them together to give us an A, which is the predicted annual soil loss in either tons per acre per year or megagrams per hectare per year, the international units. So we're going to follow figure 14 or actually box 14.1, page 513. So we're going to kind of be going back and forth in this section between page 507 and page 513 to help you understand how this equation actually works. It's actually a really good learning experience for you to understand how we put all this stuff that we've been learning this semester together to predict whether or not we're going to have a high erosion amount or a low erosion amount based on climate, based on soils, based on slope, based on how we practice cropping on that field. So in this case, the first thing that we do is we start out with this R factor. Okay? This R factor is what we call rainfall erosivity. Okay? Rainfall erosivity. And if you look at figure 14.7 at the top of page 509, you see a map of the United States with a bunch of lines on it. And they're not topography lines, they're basically climate lines. And even more specifically, rainfall lines, precipitation lines. And so these lines explain to us that in the West, for instance, in Idaho, Montana, Wyoming, Utah, Nevada, Arizona, New Mexico, Colorado, we have very little rainfall, or very little rainfall that would be of high enough velocity and duration to impact the crop production that we're doing in these areas. You move to somewhere like Florida, and all of a sudden you've got huge amounts of rainfall that can do severe damage on fields if they're left bare. So in a place like Wyoming, you see that we have a rainfall line that denotes 10. Our R factor there is 10. Okay, and then you move down to Florida, and you see you have a rainfall factor of something like 450 or 500 or 600, and that becomes your R factor. In this case, we're going to take, let's see here, we're going to have a location in Iowa on a Marshall silt loam. This is from box 14.1 on page 513. Location in Iowa on a Marshall silt loam with an average slope of 6% and an average slope length of 100 meters. The land is clean-tilled and fallowed. That little paragraph gives us enough information to go through this calculation and determine what sorts of erosion we can expect in this area. So our R factor in this particular place in Iowa, you can see on this map. This map is in not international units. It's in standard English units. And we're going to be doing this calculation in international units, so that's why you'll see the difference. You see that we're going to pick out 150 for our erosivity factor, and if you trace one of those lines, if you're looking at Iowa and you trace one of those lines back, you'll see that it corresponds to 150. So we're going to pick 150. And when we get the international units, it's going to actually be 2550, and that 2550 is going to be the number that we start with, and that's you can see in figure 14.7 that's a megajoules per millimeter per hectare per year. So you can see that we're starting off with a pretty big number. And this big number, what we're going to do with this big number is we're going to begin to take it and multiply it by each one of these factors and end up with, hopefully, something that is smaller than 2,550. Okay, so you can think about this as being taking a big number, multiplying it by other numbers that will hopefully give us a smaller number in the end, because the smaller this number, the smaller amount of soil we're going to lose from that particular field. Okay, so that's our R factor. Draw a line here, so there's our R factor. Our K factors are soil erodibility. So this takes into account different types of soils. We read that we're on a Marshall silt loam. So if we look at table 14.1 on 509, you can see that the third soil down there is a Udall Marshall silt loam. So that's a mollisol Marshall silt loam in Clarinda, Iowa. And you can see that the K factor, the soil erosivity factor, is 0.044. So we'll put that down here, 0.044. So the very first thing we do is we're multiplying this really big number by a really small number. Okay, so we're going to start to cut down that really big number in the midst of going through this complete equation. Okay, so we've got that. Now we need to think about this LS factor. That's the topographic factor, the length and slope influence on soil erosion by water. So you can see that we've got a slope of 6% and an average slope length of 100 meters from our problem. We're going to be turning to page 510, equation 14.8, and we'll be taking a look at the moderate rill to interrill sites, and that's basically the moderate ratio between the rill erosion that might happen on that site and the sheet erosion that might happen on this site. If we take our numbers, which are 6% slope with an average slope length of 100 meters, when we follow that along, what we'll see is that we're going to gain a factor of 1.7. Okay, so 1.7 for our LS factor. Here we go, 1.7. That becomes our LS factor. Okay, so we've taken into account the length and the slope, the topographic factor. And then finally we come to the C factor, which is a cropping factor. What sorts of crops are we growing on there, both in terms of cover crops and the crops that we're actually growing on there from year to year, and what we're doing in between those times. So your problem says the C factor is 1 since there's no cover or other management practice to discourage erosion. Table 14.2 notes that when you do different kinds of practices, so permanent pasture, for instance, would give you a C value of 0.003, really, really small. So we're taking these big numbers and we're going to multiply them by a really, really small number and come out with a much smaller number. We have some rotation numbers and things like that. If we don't indicate in this equation, if we have a field that doesn't do some version of this, doesn't do some sort of practice to reduce erosion in terms of its cropping practices, then we just give it a 1. Okay, so that just means we don't do anything to I want to say improve, but that might not be quite the right word. We don't do any of those cover management cropping practices that help us to control erosion. Finally, we've got the support practices or other sorts of erosion control practices that aren't actual growing of crop practices, and so we see things like contour farming, terraces that may be put into place, strip cropping, grass waterways, these kinds of other practices that aren't necessarily growing of the crop practices or residue practices left there. Your equation says, your box 14.1 says, if we assume the tillage is up and down the hill, the p-value is also 1. Okay, so we don't do any contour practices. This is in table 14.3. We don't do any strip cropping practices. We don't do terraces, and we don't. There's a sub-factor for outlets of the terraces that are moving water one way or the other. So we're not doing any of that. So we don't get to have a factor that reduces the number. If we had one of these factors, for instance, if we're in the 3 to 8% slope. If we had some kind of strip cropping, or if we had terraces in there, we might be able to further reduce this. But since we don't have any of those practices, we just say, well, we don't do any of that, so it is just 1. Okay. Once you do all this multiplication, you'll come up with a number 191 megagrams per hectare, or 85.2 tons per acre. And again, these are all per year, on a per year annual basis. Okay, 85.2 tons per acre. That's a lot of soil. That's a lot of soil to lose from a field every year, or at least have the possibility in a normal year to lose that much soil in a field. So now you can start to see that if we do that every year for 25 years, all of a sudden you're up against losing a huge amount of soil to simply rainfall happening on your field without any other factors. Just your normal practices plus rainfall equal this kind of loss. Well, this can be reduced. You can reduce this if you begin to look at these tables and see what practices are available. For instance, no-till. No-till farming might be able to reduce this, leaving a high amount of residue on your field. Terraces or contour farming even can begin to reduce this. And you'll work a little bit in your lab this week on one of these problems. You'll be doing it in the English units, so be ready for that. And you'll be doing the exact same thing that we're doing here. Only we'll have some factors change. We'll make you do this once, and then we'll go back and maybe change this factor or change this factor and see what happens to our to that final product.